Yes. So this was the slide, right?
Yeah, that was the slide.
Yeah. Thank you, Andre. Yeah. Thank you, and sorry for the glitch. And we will ensure that that is not repeating anymore. Yes, the very first technique we'll be seeing today is step potential voltammetry, which is nothing but our conventional chronometry, in which what we do is that we step up the potential from an initial potential, which is usually the OCV, and to a desired potential at which our reaction is happening. Okay, so this is what we call step potential voltammetry, because we are stepping the potential from an initial potential. So this is the conventional name, but very recently we use the name, and which is very widely known to anyone, the name of chronoamperometry, which means that we monitor the current with respect to time. So that is what we are doing here. So in sense, it is totally different from what we have seen with LSV or CV, because those two techniques are transient techniques, and in which we sweep the potential from one point to another point. In between, we measure the current response of the interface at all the potential according to the scan rate what we set. So depending on the scan rate, the shape and structure of the LSV or CV will vary drastically, particularly when it is a diffusion controlled reaction. Okay, but in the case of charge transfer control reactions, we have seen that the effect of scan rate is negligible, and it almost does nothing in the current observed at the vertex potential. Okay, so that is how this. Okay, yeah, I'm sorry, I have to make someone as a host, yeah, so that they can take care. Yeah, suppose I'm making you a host again. Yeah, please take care. Yes. So let me begin. So that is how we distinguish the steady state chronoamperometry technique from LSV and CV. So in chronoamperometry, what we do is we step up the potential from initial potential to another potential, in doing which we measure the response of the interface in terms of current with increasing time. Okay, so depending on the time, the current will also vary if the reaction is particularly diffusion limited one. In the case of charge transfer limited reactions, you will not see any drastic change in the current density if your catalyst or the interface is stable enough to carry out the reaction at the stepped up potential. So that is why we use chronoamperometry to test the stability of our electrocatalyst used in charge transfer controlled energy conversion reactions, and we measure the current response for over a period of time, like a few hours to few days. If there is no change at all in the current density after certain hours or days, we'll claim that our catalyst is the best in stability. But there are also two more possibilities in which we can encounter with even charge sensor control reactions. One is that there could be some declining in current density, and also there could be some increase in current density with increasing time. In the case of charge sensor controlled reactions too, when we record chronoamperometric response. So the reasons that are usually behind such declining is that the deactivation of the catalyst and surface poisoning, and also leaching of the catalyst material. But the increase in current density is usually because of two reasons. One is the in situ activation of the catalyst or increasing wettability of the catalyst. So these two things can result in an increase in current density in the case of charge sensor controlled reaction while we record chronoamperometric responses. And there is also a possibility when we use three-dimensional electrodes like foams, foams and carbon cloths, and also titanium mesh. When we use these three-dimensional electrodes, what happens is that even though we dip just the desired portion of the electrode into the solution, because of the capillary action of the 3D structure, the electrode diffuses or it reaches a larger area than what is actually dipped into the solution. So in essence, we are exposing much more area than what we actually wanted to expose, so that you will see such an increase in current density after a certain time of performing chronometry. So these are the instances where we see a change in current density in the case of charge transfer controlled reactions. But in the case of diffusion controlled reactions, a declining current density is inevitable with increasing time, because we know that in diffusion controlled reactions, at the very starting point, so at the very first point, when we step up the potential, the interface is having 100% availability of the electroactive species, which is getting reduced or oxidized. Okay, so initially, when you step up the potential, you will see always a high current density, which will keep on decreasing in an exponential fashion. Then it will also attain a steady state after a certain point. So you will see this declining region is very important in the case of diffusion control reaction, because we will not know the declining what we see in the diffusion control reaction during chronometry is due to capacitance or the diffusion, the growing thickness of the diffusion layer. So this is very important in the case of diffusion control reaction, because people always care much about the diffusion layer thickness, particularly in diffusion control reactions used in electrochemical sensors, because that is what will also influence the limit of detection, lower limit of detection of your material, which is sensing the particular analyte. So it is very important. So how we do is that we simply use the Cottrell equation to distinguish the current that is due to capacitance and the current that is due to the Faraday reaction. So how we do this is that we simply plot the current response against the square root of time. So if you plot the current response against square root of time, for all Faraday response, you will be having a linear decline in current, but the capacitance current will show you an exponential decay. So that is how you can easily distinguish the diffusion limitation effect from the current what you observe in chronometry. So this is what called the Cottrell analysis of step potential voltammetry. So then we have double step potential voltammetry, which is nothing but we are going to step down the potential from the potential where we have just stepped up from the initial potential. In essence, it is just like performing CV by reversing the forward scan what we perform in LSV. So in LSV, what we do is that we just sweep the potential from an initial potential to a vertex potential, and we just keep it there. Or we just terminate the analysis. This is LSV. And in case of CV, we reverse the scan again back to the initial potential. The same is true in the case of double step potential voltammetry also. Here, we step up a potential and we also, after keeping it for a while there, and we also step down the potential to the initial point. So it is just like cyclic voltammetry, but in this case, we do at constant potential. So we are not sweeping the potential. So that is the main difference. So in the case of charge sensor controlled reaction, what you will be seeing here is that if there is no backward reaction in the initial potential, you will not see any current. You will just see an increase in current initially, and that will be stabilized until you step down the potential. But in the case of diffusion controlled reaction, such as this one, you will see this declining, which is in accordance with the Cottrell equation. And when you step down the potential again, where the oxidation of the reduced product occurs, you will see a similar declining in the oxidation current. So just by quantifying the charge which is passed in the reduction and the oxidation process, if you keep the time the same for the stepped up potential and the step down potential, you can actually find out whether your reaction is reversible or irreversible or quasi-reversible. And you can also technically quantify how much how much of your initial analyte is reduced and how much of the reduced product is converted back to the initial reactant, analyte. So this is how double step potential voltammetry is used in the case of quantifying analytes precisely. So in the case of charge transfer controlled reactions such as OER, what we see is that when we step up a potential or step down a potential, we don't see any such exponential decay in current density because there is no role of diffusion control, right? So what we see usually here is a stable current density. And this is how we use step potential voltammetry to show the stability of our material at various potential for a limited period of time. So you can always perform a single step potential voltammetry, which is nothing but our chronometry, to show the stability. But if you want to show the stability of your electrocatalyst, which is performing the charge transfer controlled reaction over a range of potential, and you also want to show what happens when you lower the potential bit. So this is how you do it. Step up a potential at a regular interval, and also you can step down a little to show the current density is stable enough in order to qualify your material to be stable for a wider potential range. So that is how we use the potential voltammetry in assessing interfaces that are used in electrochemical sensors and in assessing interfaces that are used in charge transfer controlled energy conversion reactions. Okay, so now we have arrived at the third technique of the day, sampled current voltammetry. So sampled current voltammetry is an age-old technique. It has been in use for more than a century now, actually. But very recently, since the evolution of transient techniques, LSV and CV, despite having a lot of reliability issues, particularly with the CV and LSV, people have almost forgotten using this sampled current voltammetry. And this can be used in various ways and can actually become more advantageous than our CV and LSV what we use in our laboratory in day-to-day basis. So let me first explain what is sampled current voltammetry and how it is different from LSV or CV, what we record by sweeping the potential. So sampled current voltammetry is nothing but it is a voltammetric response that is constructed in a similar fashion to that of CV or LSV, because we have both current and potential scale, which is similar to CV or LSV. But the current response is actually sampled from many chronometry response. I mean, many step potential voltammetric response with increasing step potentials. Okay, so that is how we construct a sampled current voltammetry. So this is the basic difference between an LSV and CV. So in LSV, CV also we get a similar curve, but those curves are actually not of a steady state response. But the sample current voltammetry curve is of a steady state response. So when we talk about steady state response, right away you can, after correcting the IR drop, you can use this response for TEFL analysis with no issues of capacitance contribution to what I can say, the exchange current density measurements and also TEFL slope measurements. Okay, so that is how sampled current voltammetry can right away become very handy in terms of calculating accurate exchange current density and TEFL slopes. And what we do is we just step up a potential from an initial potential to various potential in the catalytic turnover region. So like 1, 2, 3, 4, 5, you can just consider it as 5 different stepped up potentials for a particular reaction. Okay, so in that case, what happens is that in potential step 1, the potential is still not enough to begin any reaction, so that we see no current here. So when we reach potential step 2, the potential is just enough to begin the reaction, but not enough not high enough to make it to be completely controlled by the diffusion of the reaction. So we see an increase in current density. So until we go to the step of 4th potential, we see such increase in current density. But after the potential, the step potential that is set in the 4th step is the maximum potential at which the charge transfer control is eliminated, because the reaction is now controlled solely by the diffusion. So after this step potential, if you increase the potential or step up the potential beyond 5 to 5 or beyond 5, there will be no change in the current density, because the reaction is now completely controlled by the diffusion of the reaction. So diffusion of the reactive species in the solution. So that is how you can actually determine the potential of diffusion limitation by increasing the or stepping up the potential in step potential voltammetry. Of course, this is very easy to determine using CV, but in CV, LSV, the current response what we measure is actually the very first response what we measure here. Suppose, for example, let's assume that you are also recording a LSV or CV in the same potential region. All the current response what you measure or record in LSV or CV are this current response, which are usually higher than what is actually will be in the steady state. Okay, so that is why I keep on telling people that using LSV or CV is always a problematic approach, because it overestimates the activity, and the overestimation is sometimes huge, particularly when the reaction is also accompanying other parasitic reactions. So, and that is what I have also recently discussed in one of my papers. So why using sampled current voltammetry is far better way in assessing the electrocatalytic activity of a material, which is usually going to be used in a steady state process like water electrolyzer or fuel cell, in which we are not going to sweep the potential, right? We are going to apply a constant cell voltage or a constant current density and perform the reaction of our interest. So it is important to know the activity of our catalyst at a steady state, not at a transient state or a fleeting potential. Okay, so that is the main difference between LSV, CV, and sample current voltammetry. See, if there are people, those who are working in energy conversion electrocatalysis, and particularly those who want to use those energy conversion electrocatalysts in steady state operations, please use sample current voltammetry, because it is the right way to do. And when you construct a sample current voltammogram, you can also use it for TAFL analysis with no issues of contributions from capacitance current. So these are the advantages that usually comes with sample current voltammetry. So there are a few conditions we should be thinking of. We can either increase or step up the potential little by little, and we can see the current response, and we will be able to construct a sample current voltammogram such as this one. But we can also step up the potential at a large amplitude, right away to 5 or more than potential which is corresponding to potential step which is beyond the step 5. So in that case, current is independent of potential, because now the reaction is totally controlled by the diffusion. So it doesn't matter how much potential you increase, the current density will always will be limited solely by the diffusion of the electrolytic species. But when the potential step is very small, so the current potential relationship is given by this equation, and you can easily relate the exchange current density with the function of with actual current density when I mean as a function of over potential. Okay, so but in the case of totally irreversible reaction, so such as OER, HER, and chlorine evolution reaction, where the reaction usually occurs at a potential way higher than the reversible potential. For example, we all know that reversible potential of OER and OER is 1.23 volt, but it does not occur at this potential at all. It always go higher than 1.48 volt or even higher than that. So this is well beyond the reversible potential, which means that according to Butler-Wormel theory, we are away 120 millivolt away from the reversible potentials. So we are literally in a TAFL region. So in the TAFL region, we'll be concentrating only about the TAFL parameters like TAFL slope, exchange current density, and other things. And in those cases, the sample current voltammetry will come in handy right away. So you don't have to worry about the capacitance contribution, which you get while recording the response of your interface using LSV or CV. And in the case of reversible reaction, that is also, in that case also, we can use a modified Nernst equation to find out the cell potential with respect to the concentration of oxidized and reduced product. So that is how sampled current voltammetry can come very handy in analyzing electrocatalysts of various interfaces, be it an electrochemical sensor or as an electrocatalyst, which is to be used for charge sensor control energy conversion reaction. Okay, so this is the example of sampled current voltammetry, as you can see here. So in this study, what we have shown here is that this is the same electrode. The green line is actually the LSV recorded at 1 millivolt per second. Okay, the scan rate is very, very low, 1 millivolt per second. And the red dots, what you see here is the sampled current voltammetry constructed from various chronoamperometric response by stepping up the potential in the desired potential window. And this is the current response with the every stepped up potential, as you can see. And I sampled the current at the 100th second. Okay, and I constructed an SCV, sampled current voltammetry. So to check which response is closer to the steady state activity, we know the steady state activity can be obtained only with chronoamperometry or chronopotentiometry. Since we have chosen LSV and CV for comparison, we chose chronoamperometric responses, which were given in the blue stars, as you can see. So these are the current densities that are sampled from the chronoamperometric response recorded for 1 hour. Okay, and these are the SCV responses. The red spheres are the SCV responses which were sampled at 100 seconds of chronoamperometry. Okay, so you can see both SCV and chronoamperometry are aligning well in line, but LSV is higher than both SCV and CA. So that is why I always say SCV is better than LSV or CV in accurately assessing the electrocatalytic activity. So yeah, so this is not only for the stainless steel electrode what we have studied, and also it is an universal phenomenon. Whatever be the electrode you study, if you use LSV or CV, your activity will always be a little higher than what you actually will see in chronoamperometry or chronopotentiometry. So if you want to make precise measurements, please choose SCV as your way of assessing the activity of your electrocatalyst. Yes, and with that, I would like to conclude today's technical session. And let's move on to the discussion session. Yes, and I think today I have not turned on the host control. So if any of you have questions, you can unmute yourself and ask me. Yeah, before asking, you can also raise your hand so that it will be easier for me to ask one by one to say your queries. Yes, yes, Ms. Mowli, yes.
Hi,
Mowli,
nice
yes,
to. Sorry, this is the first time I am attending your course.
yeah, no problem.
It seems to be very interesting, and a lot of experimentalists are struggling with a lot of things that have no particular answer from anyone. First question for my side is regarding IR correction. What
Yes, yes.
techniques you have to consider IR correction?
Yeah,
Let us say if
you
I'm showing LSV, if I'm showing TAFL, if I'm showing CDL measurements, if I'm showing chronoamperometry measurements, among these, what measurements should be considered for IR correction?
So I will put your question in different words. So whatever the purpose of your experiment or whatever the technique you use, when you use a potentiostatic method, there is always an IR drop. Okay, so that must be corrected in order to represent your interface's actual activity. Okay, so that is why we do IR compensation. Chronoamperometry is also a potentiostatic method, so there is also IR drop. And LSV, CV, needless to say. And when you perform CV for CDL measurements, also there is IR drop. But in the case of CDL measurements, the IR drop is usually having a little effect because you will see if you have experience in measuring or recording CVs in a non-Faraday region with increasing scan rate. When you have very low scan rate, it will be almost perfectly rectangular. But when you increase the scan rate, you will start to see such a what I can say, a diagonal deformation in CV. So that is
Sure.
because of, that is because of your IR drop effect because of increasing capacitance. So what we should do is that we must take the uncompensated resistance value from impedance analysis and multiply the current with the uncompensated resistance value. That will result in a potential, which is nothing but the drop potential that has to be subtracted from the actual potential scale. So this is what IR drop compensation is. But in the case of OER and HER, what I see why people are struggling in performing 100% IR compensation is that they take uncompensated resistance from the impedance spectra, impedance analysis, which is basically not normalized with the electrochemical surface area or the geometrical surface area of the electrode. But they use this pristine, I mean, as occurred uncompensated resistance value to correct the IR drop of a normalized activity. So that is the first mistake everybody does. As far as I know, most of them are doing this mistake because that will result in a curve which is declined or which is inclined backwards, which is totally unacceptable. But this happens.
Sorry, what do you mean by normalized
the
curve?
normalized means, normalized means nothing. When you use an electrode which is lesser than 1 centimeter square area, okay, and you measure the current density and you divide the current density by the electrode area, right?
Okay, yes. Like we usually use 1 square centimeter, so that is not our thing. But you understood your point.
Yes. So when people study their reaction with electrodes lesser than 1 centimeter square area, what happens is that they use the non-normalized or unnormalized resistance value to correct it. So in that case, it results in a inclining LSV. But there are also cases when the electrode area is just 1 centimeter square, but the resistance value is too high, so that it results in a high amount of dropped potential. So when we correct it, it also results in such inclining. So in that case, it is impossible to correct the LSV for 100%. Okay, so in that case, it is okay to perform partial IR correction, but be informed that you should never use this partially IR corrected LSV or CV for TOEFL analysis. So this is the thing you must be looking out for. May I know the resistance? You were the one who asked me in.
Yes.
Okay, I remember now. Yeah, thank you. And may I know the resistance value and the highest current density you obtain at vertex potential?
Well, I'm working for HER using ruthenium, let us say.
Okay.
And then I do a sweep from positive of 0.2 to minus of 0.4.
Okay.
And then the biggest problem is in my EIS, I see a resistance of 2.7 to 3 ohms. Even that is affecting my curve to move in the reverse direction at let us say at 0.2 volts, minus of 0.2 volts. I started seeing it. If I do 100%, I started seeing it like curving inwards. On an increasing. So that is the reason I moved to 85% correction, let us say. I'm still not having a right point to say in the paper or for a reviewer when he asks me why you choose 80%, 85%. If I say it is moving inwards, then they might say you are doing wrong.
No.
How to defend is clueless.
They cannot say that you are doing wrong. I guess because your material is based on ruthenium, your HER current density is very, very high at minus 0.4.
Like let us say even minus 0.2, you might have possibility to see more. But the only thing is this internal resistance. When you touch internal resistance, you will see exceptional results. So the fact comes over here is like who is responsible for this higher resistance? Because the support is conducting, the support is conducting, the catalyst is ruthenium, and still you have a higher resistance that is showing up.
Yes, yes. And you might have to work with the catalyst modification techniques. I don't know what technique you use, or the binder you use, and the substrate electrode you use. And these things also matter. So you can try reducing the solution resistance. Also, you can try to place your reference electrode as close as possible to your working electrode. And avoid having many connections in the circuit. Because I know people use a lot of crocodile clips for making connections. So that also sometimes can cause increase in uncompensated resistance. And also ensure that your crocodile clips, what you use for connecting the electrodes, are not corroded. Because the resistance is not only coming from your catalyst layer, it is from all around the circuit. Okay, so these are the few things which you can do to lower the resistance, uncompensated resistance down, and you can avoid such inwarding or inward inclining of LSV. Yes.
True. Only with this 0.2.5 ohms, I am seeing this. And the problem is, like,
don't be stressed about having 85% correction, because as long as you have not used this partially airdrop corrected LSV for TOEFL analysis, it is nothing wrong. And in my paper, which I published on the precise evaluation of electrocatalytic activity in energy environmental science, I have said this: when the current density is very high, even with smaller uncompensated resistance, it is impossible to perform 100% IR compensation. In those cases, it is okay to perform partial IR drop correction, but we should also mention it for how much percentage we performed it. So that is the only thing we needed, and that is usually accepted. So you don't.
And do you have any value that you have to have the internal resistance? Let us say you try to hold your electrodes in such a position, try to minimize the internal resistance. Do we have some value of the lower the internal resistance? Because fine. Understood.
There
is no such thing.
There is no such thing.
Because from Haramello papers and these papers who have made this kind of a total analysis of a lot of samples, they have internal resistance of 8 ohms. I'm surprised how they can't see a kind of duck-shaped curve coming backwards with that 8 ohms, but still, okay, fine. They have done this, okay, cool. But somehow with my lower thing, I am feeling this. And the second thing is, in CDL, you say that, don't you say to use IR or not?
It is usually not, doesn't matter, because to find out the CDL, you fix a common potential, not the whole range, right? So we fix a potential which is usually in the middle of the chosen region, which is not usually affected by the scan rate or the IR drop. Moreover, we are measuring the difference in current density, right? Not just the anodic part or the cathodic part. So when we measure such a difference, that effect of IR drop will be minimized. So you don't have to.
Does this has any influence on the area when you are comparing several samples? Let us say if some sample you couldn't manage.
Since we are doing the same for every sample, so it doesn't matter.
The area doesn't matter for CDLs. CDL.
I'm not saying that the area doesn't matter. The area is actually what determines.
Sorry. No, sorry. I'm sorry. Completely sorry. Okay, but let us say if I say that in CDL you are trying to measure your current where you see a straight line either in the anodic current side or cathodic current side. Do these two have to be at the same potential point, or you are expecting that you are working in a non-Faradaic region, so you choose different potential for anodic scan and different potential for cathodic scan and try to evaluate?
No. It should be the same potential. Yes.
And you claim that you are working in the non-Faradaic region. So how you define that?
Yes, because in the non-Faradaic region, when you change the potential slightly, the way the rate of adsorption and desorption of the charged species in the solution will also vary. The amount, the quantity. If you choose a different potential for calculating the anodic charge
Anodic charge and different potential for cathodic charge.
Cathodic charge, you are actually determining a two different potential, and the charge is of course going to be very different from one another. So that is why, to avoid all these things, we choose the same potential for both cathodic sweep and anodic sweep, and we usually subtract, we usually take the difference so that it is the total charging and discharging current, and we get 2 CDL. This 2 CDL can be divided by 2, and you can get your CDL. So this is the easiest and more
more reliable. The thing is, like, I start from a rectangle, and then with the higher scan rate, I'm going to get spindle in the sense like an eye, but with a kind of like the degree of angles keeps on changing, and it goes to 45. So you see a kind of a curve rather than a straight points to get a straight line. So, like, who is responsible for that? That's the reason I am thinking, okay, non-Faraday region, let us think that we are seeing a current at a straight line. So why don't we choose for anodic a certain potential and cathodic certain potential if we are thinking that is straight line?
And in that case, I have 2 suggestions. Avoid the highest scan rates, which you with which you see such a change in angle towards 45. And it does not matter that you should go for the highest scan rate always. You can also make smaller increments like 1 millivolt, 5 millivolt, 10 millivolt, 15 millivolt, and 20 millivolt. Still, you will have enough data points to calculate your CDL value.
Okay. Even you can go for 1, 5 also.
It doesn't matter. You don't have to go 10, 50, 100, 150, 200. It doesn't matter. So all that you need is, you need a current scan rate axis. So that scan rate can be anything. The increment is something what you decide. So no one can decide what should you use and what should not be used. So it doesn't matter. When you have such issues with the highest scan rate, avoid going there, and because that is no one's fault. It is because of the IR drop and the increasing capacitance, and there is also the potential delay because of highest scan rate. Because all these techniques are carried out by controlling the potential in the interface, which is not possible actually. That is why.
What is your comment on CDL when you do at 2 different potential ranges in the non-Faraday region?
That is in my opinion, that is wrong, because that is actually meaningless.
No, I mean to say, like, for a sample, let us say you take CDL from X to Y, and then you take CDL from Z to A. And do you think that CDL will be the same?
No, not at all. That's my point. No.
Then your electrochemical active surface area species you are saying, when you do a CDL calculation from X to Y, will be different from
exactly,
the other part.
Exactly, that is what I have been telling you, because it is potential dependent, and the electrochemical surface area what you get from CDL is not fixed, because it is potential dependent value, and the electrochemical surface area will also vary. For the same catalyst, even if you just move the potential window of your study, you will get different values of electrochemical surface area. That is why.
So basically, what you are saying, the area is a comparative.
Relative.
Comparative view, relative view of different catalysts at that place only.
Yes. So when you fix the same potential for all your catalysts, then there is some reasonable comparison. But when you choose different potential, it is not reasonable.
So you cannot compare this with the UPD measurements under potential deposition with copper.
UPD is totally a different technique, and that is way far accurate than CDL. And with UPD, what you get is actually electrochemically active surface area. In CDL, what you get is electrochemical surface area. There is a big difference between these two, because electrochemical surface area is something that is determined depending on the adsorption and desorption charge, where there is no electron transfer. But UPD, it is pure electron transfer reaction. It is Faraday, and it completely depends on how much adsorbed hydrogens are present on the surface. So that is the exact electrochemically active surface area.
Okay. In UPD, is it important that your baseline from sulfuric acid and the next curve when you get from sulfuric acid to copper salt, the baselines should coincide, or there is no rule that they have to coincide?
It should usually coincide. If it doesn't coincide, you can actually take the region where the current is almost flat. It doesn't matter.
Okay. Okay.
Yeah, but
Okay.
it should usually coincide.
Yeah, theoretically, yes.
Yeah.
Because like you are using sulfuric acid in both the
Yes.
cases.
Yes.
But
Yes.
who is responsible? Is it internal resistance when you
Yes.
change
Yes.
the
Of course.
change that
Yes.
system
Potential
to
delay.
some other
Yeah.
system?
Yes.
Who is
Potential
responsible
delay.
is difficult to understand.
Yes. Potential delay and your resistance. These two are the reason why you see such a variations with increasing scan rate.
So do you think people try to move the curves so that they fall on each other?
Oh, that I would not suggest.
Comment.
Yeah, no. That I
No,
would not.
because like I see two different kinds of papers where some people show they don't align, some people show perfect alignment. Well, coming to that, like there are who are the perfect papers that we can use for CPD, this UPD, but
Yeah.
still they have a kind of a perfect correlation of baselines. So I was surprised, like it is the internal resistance correction they do over there also, or
No.
how they
I am not sure about it. Yeah,
okay.
let me do some homework, and if you can join us for the next session, I will be able to give you a detailed response on that one.
Sure.
Yeah.
And then when you use a catalyst which has sulfur in that, like let us say iron sulfide or the sulfide, when you do HER, this sulfur will goes off and then it comes to oxides. And then when you use a CA, you keep seeing an increase in the current density. This is due to the corrosion of or changing of the catalyst. Or you say that wettability, activation, and
Yes.
some other part you said. So this part of changing the catalyst
No,
from
catalyst
sulfide to
change.
oxide.
Yeah. The FES in case of metal chalcogenides, the chalcogenide site is very important because they act as the proton trapping sites because of its because of its electronegativity, higher electronegativity than the metal sites, so that it enhances HER. But when we lose those chalcogen sites into the solution as oxides of chalcogens, we obviously lose some activity. In those cases, we must see a decline in current density. But if you see an increase in current density, there could be some other reasons. Like there could be formation of heterostructures. Your sulfides and selenides can be exchanged with hydroxide, forming metal hydroxide and metal sulfide heterostructure. These heterostructures are usually better active than the pristine hydroxide or pristine chalcogenide catalyst. And also, it also depends for if your reaction is HER, and it also depends what type of counter electrode you use. If you use platinum,
Graphite.
Yeah, then it is out of the picture. So graphite cannot influence on the HCR activity during chronometry. And you must be looking out for the capillary action. May I know the substrate electrode?
Substrate is either a graphite sheet or some carbon sheet.
Yeah, they are all known for capillary action.
True. So how do you suggest to come out from this capillary thing?
Yeah, you can mask the rest of the area using hydrophobic sticky tape.
Sticky tape?
Yes. Or yeah, that people do. And also there is Teflon tape, you can hold your carbon substrate on a rigid support like OHP sheet after leaving the desired area which you want to dip into the electrolyte solution, and you can use the Teflon tape to wrap it around. So that the Teflon tape is highly hydrophobic. It will help you to avoid such capillary action and excess wetting. Yes.
Thank you very much. Sorry for consuming a lot of your time, but if there is anything, I'll try to text you. Okay?
Yeah. Sure.
Many thanks.
Okay. Yeah. You're welcome, and you're welcome to join us in all the upcoming sessions. Yes, Mr. Abdul Karim.
Sure.
Yeah, please go. Mr. Karim?
Yes, sir.
Yeah.
Sir, like my question is like when we are doing IR drop correction. So yes. I already once asked you, it's like people are doing 85%, 95%, 80%. So what is the exact correct thing actually? Like how much we need to do? So, and how in an instrument we can do that, or manually we need to do that?
Yeah, I already answered this, but I'd repeat it. Manual IR drop correction is always better because it won't give you difficulties in correlating the activity. And second thing, performing 100% IR compensation is always the best practice. But there are cases in which you cannot do that. So, like the one Dr. Taluri Mahuli just told us. So, in those cases, you can perform partial IR drop correction, but you should be cautious not to be using this partially IR corrected LSV or CV for TEFL analysis. And also you should mention the percentage of IR drop compensation in your paper. So these are the two things you should be looking out for when you perform partial IR drop compensation. But there is nothing, there is nothing wrong in partial IR drop correction, as long as you are not going to use that partial IR drop compensated curve for TEFL analysis.
So how we can do that partial this IR drop correction?
Yeah, that is nothing. If suppose, let's say your uncompensated resistance is 1 ohm. If you use the whole 1 ohm, this is 100% IR drop compensation. If you use just 0.9 ohm, it is 90%. 0.8 ohm, it is 80%.
Okay, so like if I'll be running some impedance and this resistance, I'll be getting some like solution resistance.
Yes, yes.
So that resistance I need to put and need to run that LSP again.
Yes. If you take the whole resistance, it is 100% compensation. If you take 90% of it or 80% of it, it is called 80% or 90% IR drop compensation. That's it.
Okay, thank you.
Yeah.
And this thing like impedance already like in last class I asked you. So as you told like you need to give some potential, so then only your circuit will fit like a half circle. You'll get.
No, not some potential. You have to set a potential where your reaction is actually occurring. HCR,
Yes.
In that region.
So similarly, I tried. I got the full like half the circle also.
Okay.
But some places I have read like some OCP value, some OCP potential they'll be putting there. So I need.
No. OCP, people always confuse this thing with the OCP. We must understand why we are, first of all, using electrochemical impedance spectroscopy in energy conversion electrocatalysis. The main reason why we use here is that we want to compare the activity trend in terms of RCT. Or, in other words, we want to justify the observed activity trend in terms of RCT, right? So, when you want to justify the activity trend, you should be recording your EAS data in a catalytic turnover condition. In OCP, there is no catalytic reaction occurring. So how can we compare? We will not even get an RCT at OCP. In that case, how can we be able to compare different RCT values of all the control sample and our catalyst studied in the reaction of our interest? So that is why it is always very important to set a potential in the catalytic turnover condition and measure RCT value for all the catalysts at the same potential and compare it. So this is a reasonable comparison. But when you perform such EAS analysis at OCP, where there is no reaction occurring, which means there is no charge transfer. When there is no charge transfer, you will obviously not see any charge transfer resistance. So that is why you are not able to see semicircle. So don't worry about this OCP thing. If somebody stated in their paper that they have done OCP and still they were able to see semicircle, I would say that they are lying, particularly in the case of HCR and OER. It cannot be seen unless otherwise their OCP is already in the catalytic turnover region. For example, if their OCP is already high enough to perform HCR or already high enough to perform OER, but that cannot be also the seen here, because this means that their material is able to perform the reaction of interest without applying any energy, which is impossible. So if anybody stated in the paper of an HCR report or OER report that they have conducted EAS analysis at OCP, you simply still they were able to see semicircle, you simply assume that they are lying.
Yes,
it cannot be. Yeah.
And sir, like I'm mostly I'm working in the HER. So like from the LSV at a 10 milliamp per centimeter square current density, what over potential I got. So that potential I'm giving to run impedance. So in that I'm getting that semicircle, so half circle. So is that correct or not?
Yeah, you don't have to set the same potential at which you get 10 milliampere. So I would suggest, because when you study a set of catalysts, your highly active catalyst will be able to deliver 10 milliampere current density at a very low over potential. But
Yes,
some
sir.
of your controls would have not even started HCR at that potential, right?
Yes, yes, sir.
So in that case, for your control sample, you will still not see any semicircle. So what
Yes,
I will suggest you is that select a potential at which all of your controls and your catalyst are having some HCR activity.
yes, sir.
Okay. Yeah. Then you will have semicircle for all your samples. Then you can easily compare the RCT value. So if you set the 10 milliampere over potential for your catalyst, and if your control samples are not even catalyzing HCR at that potential, it will be again going to be meaningless.
Yes.
Yeah,
Okay.
so
Thank you.
it
Thank you very
doesn't
much.
matter. Yeah, it doesn't matter. Select a potential in which all the control sample and your catalyst are having appreciable activity. Yes.
Thank you, sir.
Yes. Mr. Mahesh Kumar, please go.
Yes, sir.
Yeah.
I'm actually, sir, I'm working in electrochemical sensor. I tried to detect heavy metals by using a polymer matrix, sir. In that matrix, I will detect simultaneous detection also done in some papers, sir. If I'm trying to detect a simultaneous detection of cadmium, lead, mercury, once if adding addition of small concentration, it will detect 3 metals, sir. But increasing the concentration, the detection limit is decreased, sir. Here I tried with a single metal ion like lead with lead only. It will show lead pick high detection limits. What is the problem, sir?
So it is mainly because your simultaneous detection, you have all lead, cadmium all together, right? It is because of
Yes,
the
sir.
interaction of the other ions with your electrode surface.
Oh, yes.
Yeah,
And
yeah,
another
that
one
is the
is
reason.
yes,
Yeah,
sir.
yeah.
What is the best selectivity method, sir? If I'm using a CV also for selectivity study, and after I study the DPV also, sir, but there are so many difference in that 2 systems.
Yeah, PPV is the best of all, I can say, particularly when you want to study selectivity towards multiple
Yes, sir.
ions. Yeah, because that will give you precise location of potential at which they are oxidized. In CV, the oxidation reduction peaks are usually overlapped, particularly when you go for higher concentration or higher scan rate. So that is the reason why we use DPV. And yeah, we'll be discussing about DPV method next week. And if you can
Yes,
join,
sir.
well, I will explain it in detail so that you can use that to
Yes, sir.
reduce your catalyst selectivity towards the simultaneous
Yes, sir.
detection of your analytes. And
Yes, sir. And
as for your first question, I would say that it is the interaction of multiple ions with your interface. That is why you see a lowering limit of detections, LOD value.
yes, sir. Yes,
Yeah.
sir.
Yeah.
And one more question is, if one day I'm running the DPV with the same analyte, and after day I'm running repeat the same experiment, that will also differ from different detection limits.
Yes, because your solution chemistry is not going to be the same over a period of time. So when you
Oh,
have different ions in solution, for example, cadmium, lead, and mercury, they all
yes,
have
sir.
their own solution chemistry depending on the pH. If you just
Oh,
see the Pourbaix diagram of all these 3 metals, you will see at
okay.
which pH and which potential and particular potential, you don't have to worry about the potential because it is going to be OCV
Yes,
in term, when it is just the solution. So pH matters. So at that pH, the metal ion, what you studied to, what you wanted to
yes, sir.
study, may either
Yes, sir.
be stable, I mean, maybe in the solvated state itself. Some cases it may deposit as a
Oh,
precipitate, and some cases one ion can induce the oxidation and reduction of the another species in the solution, so that the chemistry changes. For example,
yes,
if you have cadmium Hg2 plus and
yes,
Pb2
sir.
plus, the Pb2 plus can be Hg plus and Pb2 plus. Pb2 plus can be oxidized to Pb4 plus by Hg plus.
Yes, sir.
So there are such thing when particularly you have more than one metal ion in the solution, and we also have to look into the standard redox potential values of each cation, so that we will be able to determine beforehand what will happen if we keep these two cations in solution in the same environment. If the potential difference between the standard redox potential difference between these two species are large enough to cause reduction or oxidation, it is not a good idea to keep them in the same solution. But you can add them together at the time of analysis. You should not keep them aging together in the same solution. There are so many other, and also your electrode. And your electrode, even if you modify a substrate electrode with the same catalyst and keep it for different time of drying, each electrode will behave in different ways. So it depends on various factors, but mainly the solution chemistry of the reactive species and the electrode surface. So these two, you have to do it every time freshly. So that's the only way you to get good reproduced data.
Okay, sir. Okay, sir. And one more question is, if that pH is different, means the potential also different, sir.
Yes.
But that current deduction also slightly increased or decreased.
Yes.
That problem also.
Yes. Because for all potential from Nernst equation, we know that cell potential is pH dependence, right? So with change in pH dependence, your potential will also be varying. And with
sir,
the pH,
if potential difference means also current also different, sir?
Yes, and that can happen because depending on the pH, your catalytic activity may increase or decrease. So peak potential change is mainly because of pH, but pH can also indirectly influence your activity. The peak potential change does not usually cause the reduction or increase in current density. By theory, it doesn't matter. The current should be the same for the same amount of analyte. But the increased pH or lowered pH can also affect the activity of your material, so that it can cause fluctuation in current. But the shifting of potential is mainly because of pH.
Okay, sir. Thanks, sir. Thank you, sir.
Thank you very much. Yeah, I think we don't have.
Can I request a small clarification?
Maybe after I answer the questions in the chat box.
Okay, sure.
Yeah, thank you. Screen print. One of you is asked, I want to ask a very basic question, which electrode is better, GC electrode or screen printed electrode on autolobe instrument? So it doesn't actually matter. It depends on for what application you are going to use that electrode as a substrate. So it is to be decided at your own discretion. I don't have a say in that. So both the GC and the screen printed electrode are having their own advantages and disadvantages. That has to be weighed in relationship with your reaction of interest. Yes. Mr. Dr. Taluri Moli, please.
Yeah. Well, when most of the people write regarding TOEFL, they don't mention either the area of current they are taking or the area of potential they are considering to compare the list of things that they have mentioned. So as per you, which has to be told, like, okay, in between the range of currents among these all electrodes I have taken to measure, to clarify the TOEFL slope, or between certain potential?
I have told this in one of my earlier sessions, because we electrochemists always follow this convention, because in order to qualify a potential region to be suitable for TOEFL analysis, the current contribution from the backward reaction or the opposite reaction should be lesser than 1%. This is the theoretical demand. Okay, but in the case of HER and OER, since we perform the analysis at sufficiently higher over potential, the current contribution because of the backward reaction, ORR and HOR, is usually and almost lesser than 1% than the forward reaction what we study. Okay, so it doesn't matter. But in the case of HER and HOR, they are not well separated as OER and ORR. So it is always important to perform TEFL analysis at sufficiently higher over potential from the reversible potential, I mean from 0 volt. So obviously when you perform TEFL analysis closer to your onset potential, your TEFL slope will be very low, but your exchange current density will be also be very low, which must be higher. But when you perform TEFL analysis at a higher over potential region, your TEFL slope will be very high, but your exchange current density will also be high. So, but for a good catalyst, we expect higher exchange current density and lower TEFL slope, which can be obtained only in the true TEFL region. So, which has to be determined based on the TEFL relationship, in which the stoichiometry of the reaction matters, and the number of electron transferred in the rate determining step matters, and also the potential region what we choose. So it must be considered. And also when you calculate the TEFL slope, never calculate from a region which is not covering a full decade. Okay, so it should cover a full decade of current density, or more than a decade is usually better. And never extrapolate TEFL line which is not covering a full decade to get TEFL slope value. These are something we must follow. And usually people don't mention these things, where they measured and how did they do. But by simply looking at the TEFL plot, we can easily find out at which potential range, and from the onset potential or the reversible potential, they have calculated the TEFL slope. And we can also come to a conclusion on the reliability of the data, what they are reporting based on the TEFL plot, what they have given.
True, but if basing on my analysis, if I choose current density as a potential region for me to measure TEFL slope, so current density is there for everyone, every comparative electrode. Even you take blank, you have that current density. Even for rest of the electrodes also, you have a current density. If I choose a range of over potential, maybe I can have current density at that potential for some electrode, and some electrode I don't have that potential, that current density at that potential. So if I say that I am taking from 10 milliamps to 30 milliamps to measure this TEFL slope, I feel like this is more reasonable than from 0 to 10 milliamps if I take the current density to measure the TEFL slope. So in some papers, they do mention that the range of current density that they take to measure all the curves for TEFL analysis. But in most of the papers, they don't show that. Because like I see, like for some electrodes, they go for 0 to 10. Some electrodes, they go for 5 to 15. For some electrodes, they go for, let us say, 10 to 15 milliamps of current density. When you want to compare, you should stick to some defined range.
So we actually cannot fix randomly, like 10 to 30 or 10 to 15. It is not in our hands. Since we calculate TEFL slope, which is nothing but millivolt of potential required for your interface to step the current density by a decade, right? It is like 0.1 to 1, 1 to 10, 10 to 100. So this is what we call a decade in a logarithmic scale, right? So how much potential is actually required for your interface to step a decade of current density up? Okay, so obviously for the smaller magnitude of increment, I mean the first 0.1 to 1 and 1 to 10, the potential required will be very lesser for your interface. And for higher current density, obviously going to be higher, and TEFL slope value is also going to be higher. And that is why we have this set of rules. When we choose the smaller decade region, like 0.1 to 1, 0.1 milliampere is so less that the backward current density, the current density because of the backward reaction, particularly in the case of HER, the HOR current can easily reach more than 6 or 7 milliamps sometimes. So when we perform very closer to HCR onset, we will not be very sure that there is no current contribution from the backward reaction. So that is why we always say to ensure a potential range where the current contribution from the backward reaction is less than 1%. Then you can always extend your potential window in order to accommodate one or more than 1 decades of current density and measure the Tafel slope. So that is the appropriate practice, I would say.
Sorry for not having the knowledge of
no.
backward reaction of 1%, less than 1%.
Yeah.
I couldn't relate this word in context to what I see in CV. Maybe you can drop me, maybe I request you by email, maybe you can drop me an email
yes,
saying what is that you are saying, because like I couldn't relate that what I see on
it is nothing. I'll try to explain it to you again. So we know in HCR have you performed UPD? You know that the backward oxidation, hydrogen oxidation current you see is actually having an exact intercept at the HCR onset for PT and other UPD having materials. So it means that the backward reaction and the forward reactions are nearly inseparable. So when we perform Tafel analysis by taking a current density, a decade of current density much closer to the reversible potential, there is also possibility that the current density is coming from the opposite reaction, hydrogen oxidation reaction. And in that case, it can also be higher than 1% of what we are actually trying to study. So in that case, the Tafel analysis cannot be done. But if you increase the over potential to farther region from the reversible potential, you basically eliminate the current contribution from the backward reaction. I mean from HOR. So in this reaction, in this case, in this region, you don't have any issues or any contribution from the HOR reaction. So then you can easily select a potential region in which 1 or 2 decades of current densities are measured, and you can perform Tafel analysis. So this is what I'm trying to say.
Oh, okay. I think that I can relate that, but
yes,
but still I'll drop you an email if you don't mind.
Sure.
Yeah?
You're welcome.
Okay. Yeah. So thank you.
Yes, Dr. Dhanasekaran. Yeah, Dr. Dhanasekaran, please unmute yourself and ask.
Yeah. Hi to all.
Yeah.
And my question is, many of them are taking Tafel from electron impedance spectroscopy also.
Yeah. That is one of the finest way.
Yes. In there, we can apply the different potential, and we can collect some, resistance value. So for plotting purpose, in which value we will take?
You have to take the RCT.
Yes.
And plot the inverse reciprocal value, reciprocal of the RCT against the potential, the set potential. Okay. 1 by RCT. Yeah, 1 by RCT against the potential.
Means that imaginary line.
No.
I have getting confused.
No. How we usually calculate RCT is that we take the difference from the 2 points, right? We have a semicircle. So when the semicircle intercepts the x-axis on the both ends, so this difference is RCT, right? When you increase the potential, the magnitude of this
RCT value
will keep on decreasing.
Okay.
Right. So which means that the RCT will also decrease. When you take the inverse, it will give you the what I can say, conductivity or the admittance value.
Okay.
Yeah, because it is impedance, we will say admittance. Okay. This admittance is equivalent to the current what we use in Tafel analysis.
Okay. And some of them using from the CV. I mean, scan rate also they are taking Tafel plot value. How? Which one is reliable?
No. CV, using CV and LSV, I will not recommend that practice because there are a lot of issues with them. And impedance is a good practice, but it is not always a better way to directly analyze. I would suggest you to do chronopotentiometry.
Okay.
Yeah, set different current density. For example, if you are performing HER, set 10 milliampere, 20, 30, like that, you can increase until 100 milliampere per centimeter square, so that you will have a full decade of current density. You will also have a range of potential. You can simply convert this.
In that on a potentiometry, suppose I running that 10 milliampere means it is giving some starting potential. We have to take the starting potential.
No. You should give the interface to stabilize its activity, and you should measure the potential at a steady state response.
Okay.
Not the starting point. Not the starting point. Steady. Yeah, not the starting point.
Okay.
Yeah.
And in my cases, for OER, I have plotting, but that Tafel plot value is giving more than 100, nearby 150. Using I was used in the substrate of nickel foam also. But I am not without IR correction. I am doing that. So if may with the IR correction, that plot it may give below. I mean, Tafel plot below 100.
It should give. Yeah, and using an IR drop uncompensated curve is not a correct way, because the Tafel equation what we have derived from the Barlow-Amel theory is theoretically having a overpotential term which is assumed to be free from IR drop. Okay, so when the relationship itself derived using a potential term, overpotential term, which is free from IR drop, we should also be using a potential scale which is corrected for IR drop. So without correcting IR drop, we cannot perform Tafel analysis. Even if we do, it is wrong. And second thing, it is not very uncommon to see abnormal Tafel slope, like more than 120. I have even known people have reported 750, 740.
Okay.
Based
on that substrate, it may be very. But for the particularly
there are a lot of reasons, Dr. Dhanasekaran, actually. Not only the substrate. If you see the Tafel slope, it is not a fixed or quantized value, because the Tafel slope value is actually directly influenced by the number of electron transferred in your rate determining step and the charge transfer coefficient. Okay. So by theory, charge transfer coefficient cannot go lesser than 0 and also cannot exceed more than 1. It should be within the range of 0 to 1.
0.5.
Yeah, okay. 0 to 1. But the number of electrons transferred in the rate determining step can be 1, or it should be mostly 1, and it can sometimes also be more than 1. Okay. So these two values are what causing your Tafel slope either to be higher than 120 millivolt or lesser than what we know, lesser than 23 millivolt per decade. Okay. So instead of just reporting the Tafel slope, I would recommend reporting the product of charge transfer coefficient and number of electron transferred in the rate determining step. That is more. That is having more information than simple Tafel slope.
Okay. Yeah. But after suppose I took Tafel slope from IR with IR correction. Yeah. But can I give the data without IR correction of the overpotential?
No, because it is incorrect to do that. So when you have an incorrect data, it is not recommended to be mentioned in the paper.
So yes. Okay.
Yeah.
Okay.
Yeah. Thank you, Dr. Dhanasekaran. Yes, I think we have exceeded the time, and it is almost 10:30 here. And I'm also having a little headache, so I would like to thank you all again for joining me here today for another session of Let's Speak Electrochemistry. And I have a request to all of you. I have a feedback form. I'll send this to all of you. And please take 5 to 10 minutes to answer the questions I asked. And I have recently become very busy with so many things because of the end of the academic year, and I have also keeping a lot of deadlines in queue I have to finish. So I'm thinking of conducting this session twice in a month or once in a month, because I initially thought that I can go on with it every week like we have been doing, but I'm not very sure. So it's all going to be depending on the feedback you are going to give. So please take some time and yes, answer the question. Yes, Dr. Dhanasekaran.
Not just like that. Now what you are saying that if no problem, monthly 1 or 2, but somewhat time extended is better because
okay. Yes. Yeah,
because for this 1 hour maximum 1 or 2% only maximum.
That's right. Yeah. So if we are going to have only once in a month, then we will think of increasing the times. Time of the meeting. Yes, thank you for immediately sharing your opinion. And also please take some time to fill in the form and send me back so that I will decide on that one. Yeah, thank you all for joining me today. Let me see you all again in another session of Let's Speak Electrochemistry. Thank you.